The routing graph created by the set of DODAG parents across all nodes defines the full set of upward routes. RPL protocol implementation should ensure that routers are loop free by disallowing nodes from selected DODAG parents that are positioned further away from the border routers. Basically, the upward routers in RPL are discovered and configured using DAG information object DIO messages. So these nodes listen to DIOs to handle changes in the topology that can affect the routing. Nodes establishes downward routing by advertising their parent set towards the DODAG route using a destination advertisement object DAO messages. So here DAO messages allows nodes to inform their parents of their presence and reachability to descendants. In non-storing model of RPL, nodes sending DAO messages report their parent sets directly to the border router and only the root stores the routing information. In case of storing mode, each node keeps track of routing information that is advertised in the DAO messages, that is destination advertisement object. While this is more power and CPU intensive for each node, the benefits is that packets can take shorter paths between destinations in the mesh. The nodes can make their own routing destinations in non-storing mode. On the other hand, all packets must go up to the root to get route for moving downstreams. The RPL messages such as DIO and DAO runs on top of IPv6. These messages exchange and advertise downstream and upstreams routing information between the border routes and the nodes under it. So as we will be going to have the hop counts and all these things, these by advertising the objects itself, so they will come down that which is the shortest path. So based on that, this is a good protocol where they can take their own decisions for the reaching to the destinations in a faster manner. The overview of that it is being shown here. The IP wireless area network. There is a direction oriented DAG is there. There is a root. RPL instance is there, that is complete setup, that is network. The ranks are there 1, 2, 3, 4, where the data is going to be get travels from down as well as up. In both directions it has been shown here. DAO and DAO messages travel both up and down the direction oriented DAG depending on the message types. So based on that communication path, the data is going to get. There is an objective function inside. What is this objective function? An objective function defines how metrics are used to select routes and establish the node rank. For example, here nodes implementing on objective function with the minimum expected number of transmissions advertise, that is METX, that is minimum expected number of transmissions among their parents in DIO messages. So much fast that we can reach basically. That is, whenever a node establishes its rank, it simply sets the rank to the current minimum expected number of transmissions among its parents. What is rank then? The rank is a rough approximation of how close a node is to the root and helps avoid routing loops and the count to infinity problems. So basically a routing table is going to consisting of ranks also, because at what time that it is going to be reached, number of hops, hop count we can say. So the ranks are going to be minimum, it is going to be reaching is fast. Ranks are going to be more, reaching is going to be time taking. Now the nodes can only increase their rank when receiving DIO message with the larger version number. However, nodes may decrease their rank whenever they are established lower cost routers. While the rank and routing metrics are closely related, the rank differs when routing metrics in that it is used as a constraint to prevent routing loops. Otherwise, if the loop is going to be there, then it counts there only number of loops. It doesn't goes out of that particular loop. So there is a failure will be there in that. Then what is matrix basically? It is. So here we can say that some of the RPL routing metrics are constraint defined in RFC 6551, which includes expected transmission count. It assigns a discrete value to the number of transmissions of a node expects to make to deliver the packet. That is the destination. The hop count is there, which are basically that it is required for the destination, from source to destination to reach. The first is hop count. Hop count is nothing but it tracks the number of nodes traversed in the path. Typically a path with a lower hop count is chosen over the path with the higher hop count. It should be minimum, that is what. Then latency. Latency is a time variation. Varies depending on power conservation. Paths with lower latency are preferred. Link quality level is another matrix. It measures the reliability of a link by taking into account packets error rates caused by factors such as signal attenuation and interference. Some packets are not going to be reached, so the time is going to take that particular count also. This is a link color. Allows manual influence of routing by administratively setting values to make a link more or less desirable. So these values can be either statically or dynamically adjusted for a specific traffic types. We have another set of things: the node state and attribute, node energy, and throughput. Because each and every node is going to get forwards that particular data, that time we need all the what is the state and its attributes and how much energy it is power is consuming. Okay, what is ultimately the throughput. So here in the node state and attributes, It identifies nodes that function as a traffic